General relativity, step by step. Last time I talked about homogeneity and isotropy of the universe. I threw out the steady state condition. I'll revisit it later, but for the moment I'm going to stick with homogeneity and isotropy. Yeah, I guess the first thing we need is to sort out a time coordinate. Now last time I made the observation that all our observers, or all the observers I'm interested in anyway, observers, can you spell observer? Observers are at rest. With respect to the cosmic background radiation, cosmic microwave background. And of course I want a coordinate system that exploits that physical truth. I think I said last time that if you're moving very quickly, if you're moving at say 90% of the speed of light, then eventually you come to the land where everyone is moving at that speed. And so the observers being at rest is a reasonable physical principle. I think that's a very profound observation actually. It was made originally to me at least, by Herman Bondi in a lecture in response to a stupid question which I asked. It wasn't the only stupid question I asked either. But he was a gifted educator, was Herman Bondi. I didn't appreciate him at the time. Right. Time coordinate. All observers are at rest with respect to the cosmic background. So my time, which I'm just going to call t, I'm going to use the symbol t, is going to be the proper time for my observers. There's just a little little detail. If these are galaxies here, I'm not very good at drawing galaxies, and there's a sort of spiral one and another one here. They're all sort of moving. They're all moving at different speeds. Here's another galaxy here. Effectively, what I'm going to do is give each of them a little clock. I'm going to give a person on each galaxy a little clock and say, okay, guys, you're going to define your own time. And that makes perfect sense. But you've got a slight difficulty when it comes to verification. I mean, if I'm here and I want to visit my friend in this galaxy here, I've got to go over there and visit him, maybe taking my clock with me. But of course I'm going to be subject to a Lorentz time dilation while I do that. But that's impermissible. That's not what we're considering, because then this observer, this is me carrying a clock to my friend who lives in this galaxy here, I'm not going to be at rest. And so I am inadmissible as an observer. So I've got no problem with considering time t being the proper time for all my observers. And that's a good start. That's a good start. It's reminiscent of the case of gravitational waves, when I made the observation that to first order there's no time dilation in a gravitational wave. And we've got the same type of situation here. We can just consider proper time for my observers, and that will do as a universal time coordinate t. Okay, so that's great. So my next step, of course, is to fix a time t and look at the spatial components and look at my spatial metric at fixed time. That's what I'm going to do. I'm going to fix a time t and look at the spatial metric at that particular fixed time, well, I guess we could just fix it at now. I guess that would be a good time. And say, okay, this is our time. We're gonna fix it now and look at it. But we can fix it at any time and think about what the universe looks like at that particular time. And then I'm going to make the observation that because of my homogeneity and isotropy assumptions, because of these assumptions here, I'm going to impose spherical symmetry. I'm going to impose spherical symmetry, and the way to do that is to make a coordinate system in which spherical symmetry is obvious. I'm going to exploit the spherical symmetry of the universe by choosing a coordinate system in which the sphericalness of the spherical symmetry is clear. I just want to make another observation. How long has this one gone on? 4 minutes. No, I'll do that in the... no, I will do it now. I will do it now. If I've got just a normal... This is the surface of the Earth, right? and I'm going to consider a nice spherical coordinate system here. That's theta and that's phi there. That coordinate system there, the r is fixed. The theta phi system, it looks like this privileges, I'll put it in quotes, privileges the North Pole. It looks like it privileges it because the coordinate system all kind of goes a bit berserk at and I guess the South Pole as well. The coordinate system goes a bit berserk at the North Pole and South Pole. It's a kind of singular point and differentiation doesn't work there. It kind of sucks. But I just want to make the observation that the sphere itself is spherically symmetric. However, when we choose a particular coordinate system, it looks like it's singling this point out here as being something special, but it's not. We could choose any point. I'll write that down. Could choose any point as the North Pole if we wanted. So, because we could choose any point, it doesn't privilege any point. Does that make sense? Because we could choose any point, we're not privileging any point at all. We could make the coordinate system what we want, and indeed we can transform from one coordinate system to another. You can't get around the coordinate singularity. You need a coordinate singularity somewhere, but because the existence of the coordinate singularity doesn't invalidate the symmetry or doesn't spoil the nice beautiful symmetry of the sphere. I just want to make that observation because I'll come back to it in a slightly different guise in the next screencast. I'm going to stop there, and in the next screencast I'm going to show what types of spherically symmetric coordinates we're allowed to use. Stop.